Let's start by looking at what happens to charges as they go around a really simple circuit. This diagram shows voltage on the y-axis and distance around the circuit on the x-axis. The charges are going to start at the EMF. It sets up an electric field and it pumps the charges up to a potential of plus V. Then the charges follow the direction of the electric field and they fall down to a potential of 0. Since it's a circuit, the EMF pumps the charges away again. And so it continues. Now let's see what happens when we put a capacitor into the circuit. The capacitor is shown here with purple dotted lines. It has two metal plates where those dotted lines are and an insulator between them. So when we switch on the EMF, it pumps charges up to a potential plus V. The charges will fall down to a lower potential, but this time they'll only go as far as the capacitor plate. They can't go any further because they can't travel through the insulator. The EMF will continue to pump charges, and those charges will continue to roll down towards the capacitor, but they'll build up. This build-up of charges starts to create an electric field. We'll call this side the positive side of the capacitor. The electric field is going to be the opposite of the direction of the electric field created by the EMF. These charges also create an electric field pointing to the other side, towards what we know as the negative side of the capacitor. The charges there will feel this field as well, and they'll be forced away. This creates charge depletion. The charge depletion on the negative side, of course, creates its own electric field, which points towards the negative plate. The two plates both cause an electric field pointing to the right inside the capacitor. So these electric fields add, and we have a strong electric field within the capacitor. However, outside the capacitor, the electric fields point in opposite directions. So these electric fields cancel. This all happens when we have moved a charge of Q onto the plus side and we have removed a charge of Q from the negative side. The reason that the same amount of charge is added to one side as is removed from the other is because charge in this circuit is conserved. Whatever is added to one side has to be subtracted from the other. Now, if the electric fields outside the capacitor are cancelling, then there can be no potential difference across the wire there. So, between the EMF and the capacitor, the potential doesn't change. However, there is going to be a big potential difference across the capacitor. That's the same size as the potential difference across the EMF. But what happens now is that the EMF can't push charges around this circuit. It can pump them up to the high voltage end, but they won't roll down to a lower voltage. Now let's put two capacitors in the circuit. These capacitors are in series because the current has to flow through one and then the other. So the EMF pumps charges up to a potential of plus V, and the charge will build up plus Q on one side of capacitor 1, and minus Q is going to be on the other side of capacitor 2 because of charge leaving. We end up with a situation where the positive side of capacitor 1 has no potential difference compared to the EMF, and the negative side of capacitor 2 also has no potential difference compared to the EMF. Now, those charges on the outside plates of capacitor 1 and capacitor 2 create an electric field. And those fields move the charges in between the capacitors. You can see the potential difference that appears. So charges will move from capacitor 1 to capacitor 2 along the wire that connects them. This will happen until there is no longer a potential difference between them. This happens when Q leaves capacitor 1 and arrives at capacitor 2. So it means that every plate in our capacitor series has a charge of plus or minus Q on it. So the potential differences now across capacitor 1 and capacitor 2 appear, but they are smaller than the potential difference that appeared when we had just a single capacitor. Now let's compare the charge on the capacitors in these situations. In general, the charge on a capacitor is equal to the capacitance times the potential difference across it, CV. If the potential difference across capacitor is less, then it means the charge on it is less. On the right-hand side, we have the single capacitor situation. That has a large potential difference across it. If we compare that to the situation on the left, the two capacitor series, they have a smaller potential difference across them. It's like the entire potential difference is spread across two insulating gaps. It means that each of those capacitors has a smaller charge on them. We can think of it as similar to a situation where we have a single capacitor which has a smaller capacitance even though it has the same potential difference across it. It's rather like if you had a single capacitor on the right-hand side and then you increased the distance between the plates. That would decrease the capacitance and weaken the electric field inside it. So we have a smaller electric field. Instead of thinking about it in terms of potential differences, we can also think about this situation in terms of work and energy. So in both the single and the two capacitor series situation, the EMF performs the same work. The work is V times Q to push a charge around. Now, whether that's the work done by the EMF or electrostatic work to move the charge around the opposite direction, the work is going to be the same. So, if we do electrostatic work, on the right-hand side for a single capacitor, the work is going to be the work against the electric force times the distance across the capacitor. on the left-hand side, it's going to be the sum of the work that you do across each capacitor. What you can see is that the force that you apply in the two capacitor series has to be less, because these works must be equal. And if the force you apply is less, it must mean that the electric field is weaker in the two capacitors. If you add more and more capacitors into a series circuit, the EMF can do less work per capacitor. It means that it moves less charge onto each capacitor, and the electric field on each capacitor becomes less. The result is that less potential energy is stored in each capacitor. So the work by the EMF that becomes stored in each capacitor is half times the charge on the capacitor times the potential difference across it. And both Q and V are going to be less. But how do we work out what is the charge or the potential difference across a series of capacitors? To find the charge on each capacitor, we're going to compare the potential differences across each of a series of two capacitors and the circuit with a single capacitor. So the potential difference over the EMF is going to be the same as the potential difference over the single capacitor circuit. And that's going to be the sum of the potential differences across each individual capacitor in the series circuit. Now, the potential difference across a capacitor is equal to the charge on it divided by its capacitance. So the charge that's on a single capacitor divided by its capacitance has to be the sum of the charges on each individual capacitor in the series divided by each of their capacitances. What we also know from before is that the charge on every capacitor in series must be equal. So let's call that Q2 capacitor series, and we factor it out. So we rewrite the equation as the charge on a single capacitor by 1 over capacitance is equal to the charge on the two capacitor series times 1 over capacitance 1 plus 1 over capacitance 2. So you can see that you can model this two capacitor series as a single capacitor as long as you let that effective single capacitor have an inverse capacitance that is the sum of the reciprocals of the individual capacitors. You can also see that once you use this formula to work out the charge on each of your capacitors, you can go back and use that to work out the potential drops across each capacitor.